Log on, tune in, find out. Another good idea from Cambridge.
To introduce the next speaker, Peter Fiebig from the University of Freiburg. He'll tell us about the Lusztig conjecture as a moment graph problem.
Thank you very much, Henning, and I wish to thank the organizers for the invitation to this program, actually, and also to this conference, and for giving me the opportunity to speak at the conference. So, so I will talk about a new approach towards a link between the topology of algebraic varieties and representation theory of various types. So there's essentially two ways that I know of relating geometry or topology of varieties to representation theory. The first way is the following. It's the Bailin's and Bernstein localization. So you take the geometry of G mod B, the Fleck variety. So G is a complex group, and B, of course, is a Borel subgroup. The geometry of G mod B is linked to the representation theory of G, the Lie algebra of G, via the Bailin's and Bernstein localization, which is just the idea of realizing the Lie algebra in terms of global differential operators of on this variety. And so you link D modules to certain representations of G. But there's an alternative approach due originally to Zergel. Here this is rather on a topological side. So you have here the topology of G mod B, and this is linked, due to Zergel, to the representation theory not of G, but of the Langlands dual Lie algebra. So the Lie algebra that corresponds to the dual root datum, dual root system, and this is done via an intermediate step, which is modules over a certain coinvariance. So the Zergel coinvariance, which is from an intermediate step, and so the coinvariants here on the left-hand side, they correspond to the cohomology of G mod B, and here they are kind of the center of the corresponding representation theory. So this is a very different link between topology and representation theory, and both ideas lead to proofs of the Lusztig conjecture in this setting. But they are very different, and also they are of course independent, but they are also very important in their own right, because if you take these two together, you get causal duality, because here you identify via the Riemann-Hilbert correspondence D modules with perverse sheaves here, and you get in the end, if you work hard enough, you get a derived equivalence of the representation theory category O of the Langlands dual Lie algebra and the original Lie algebra, a derived equivalence which is called causal duality. So one also very important point in this two approaches is that here the important objects are the simple D modules, which correspond to simple representations, and here the simple perverse sheaves, so the intersection cohomology complexes here on this side, they don't correspond to simple representations, but to projective representations. So this is a kind of idea of causal duality, which in the end links simple representations and projective representations. So the idea now is to find an analog of the Zergel approach for in the affine world. So in the affine world, we have various types of representation theories. So for example, So we have, so the idea is to apply this in the affine situation. So here we have the modular representation theory so the representation theory of the Lie algebra over a field K with positive characteristics. Very related is the quantum group representation theory, but also the non-critical representation theory of the affine Kac-Moody algebra. So this is the affine Kac-Moody algebra associated to G. And in the end, there's also the critical the critical representation theory of G hat. So in all these instances, there is work on the analog of the Bellingson-Bernstein localization. Here in these two worlds, it's the work of Bezukavnikov. Here it is the Frankel-Gates-Curie program of describing the critical level representation theory of an affine Kac-Moody algebra in terms of convenient Bellingson-Bernstein localization functor. And this is quite classical and maybe the instance that is closest to the finite world. This in this case, it's done by Kashiwara Tanisaki, who studied the analog of the Bellingson-Bernstein localization. But somehow the circular approach can be done here too in these worlds. I mean, it's kind of conjectural in this instance at least. And there, for the circular approach, you need, or it's convenient to use a new theory, which is the theory of sheaves on a moment graph. So, yes, at roots of unity. Yes, the quantum group representation theory at roots of unity. So, let me motivate the moment graph category by coming from the topology of a Fleck variety. So, for this, we choose a maximal torus. And we choose a field K. And the field K should be the base field of the theories that we are looking at here. It would be the defining field of the Lie algebra, and here would be complex numbers. So then we can define the T equivariant derived category of sheaves of K vector spaces. So this is the equivariant derived category of sheaves of K vector spaces on G mod B. And for any object here, no, we take the, I mean, we don't derive the category of equivariant sheaves, but this is the equivariant derived category in the sense of Bernstein-Lund. So, no, I mean, it's a triangulated category of equivariant. I mean, it's not a derived category of equivariant sheaves, but the equivariant derived category constructed by Bernstein and Lund. So for any object here, we can define its hypercohomology, the hypercohomology of F. And for now, I mean, it has various structures. For now, for us, at the moment, it's just a module over a symmetric algebra. So S is the symmetric algebra of a K vector space. The K vector space associated to the lattice X, where X is the character lattice of T. So this symmetric algebra will act on this hypercohomology of F. And one of the problems is to calculate, for a given specific F, to calculate this hypercohomology. And one idea, one approach, one method is the localization method. It's the following. So first, let me fix some notation. So if we have the inclusion of a subvariety, G mod B, then I define F upper Y to be the pullback of F. So it's a sheaf on Y now. And so the idea of the localization theorem is to pull back the sheaf to the set of fixed points. So G B upper T is a set of T fixed points. And so this gives a map, a pullback map, which I call I upper star from the global hypercohomology of F, so the space that we would like to calculate, to the direct sum over all fixed points of the pullbacks of the sheaf. So we take this sheaf, we pull it back to each fixed point, and the hypercohomology. So you have an adjunction map from this space to any of these spaces. We take the direct sum, and we have a map like this, which is called a localization map. This is the localization map, and so it turns out that in very many situations, this map is actually injective. And in addition, this very often is a very easy to calculate space. It's just an equivariant sheaf on one point. You just have to, well, it's in most cases we know what these stalks are. And this map is injective, so we would like to determine its image. And so the wonderful result of the localization theory, I think in this sense it's due to Goreski, Kottwitz, and McPherson, is that this image is cut out by some relations coming from one-dimensional orbits. So the image is already determined by looking just at the fixed points and at the one-dimensional orbits. So how is that done? So if we have E in G mod B, a one-dimensional orbit, then E is T equivariantly isomorphic to a copy of C star alpha, where this is just as a variety, it's C star, but acted upon via the torus, by the torus via the character alpha. So alpha is an element in X, and this is a T space via map. Well, the obvious map that maps Tz to alpha T times Z. So this alpha is actually it's uniquely determined up to a sign. So it turns out that all these orbits look like this. And so we can also form the hypercohomology of the pullback of the sheaf F to the orbit E. So now this Fe is an equivariant sheaf on E, a T-equivariant sheaf on this one-dimensional orbit, and it turns out that this is an S modulo alpha S module. So it's certainly an S module, as any equivariant T-equivariant cohomology is, but this space is annihilated by the character alpha. So the next thing, the last thing you need to construct before you can formulate the localization theorem is a map. I call it rho xe. So for any fixed point, in the closure of E, so if you form the closure of this one-dimensional orbit, you pick up two fixed points. Let's call them X and Y. So just so if you have this 2 sphere which is rotated by alpha, then it has 2 fixed points at the south and the north pole, and those we call X and Y, and the sphere is E. So this is the situation you encounter in the flat variety. So you have these 2 fixed points in the closure, and for any fixed point, you can define a map from the local cohomology at the fixed point to the local hypercohomology at the orbit. Well, this is not very difficult to construct. Okay, so now I can formulate the localization theorem. One last definition. So we are the localization theorem in the form that I want to use now was first formulated by Goretzky, Kottwitz, and McPherson in the case that K is the complex numbers. But here we need also for these applications a field of positive characteristic, but we have to exclude some bad characteristics. And the corresponding definition, or the assumption that we have to make is the following. We assume that that if E and E prime in G mod B, if those are one-dimensional orbits, and if they share a common fixed point, so if they're linked by one point in the closure, then we want that the corresponding characters, the ones that we defined here, corresponding to the orbit, so we should maybe call this alpha E, that those two elements are linearly independent in the vector space X tensor K. So in a K vector space associated to the lattice, so I write it like this. I write it like this, so they are not multiples of each other if you want. These are the images in a vector space. So this is the restriction that we have on our field. It's actually a restriction on the characteristic of our base field, and this we call the, if this holds, then we say G mod B K is a GK ampere for Goretzky, Kottwitz, McPherson. So this is the definition of the of this being a GK ampere, and Yes, characteristic 0 is always good. And also, for the finite, in the finite case, for finite flag varieties, we only have to exclude 2 and 3 in type G2, and otherwise we only have to exclude 2, but none other prime. But we will talk later about the affine case, and then this becomes very important. And yeah, so G mod BK, if this is a GKM pair, and if this cohomology space that we want to calculate, if this is free over S, if this is free, then I upper star is injective, and hence induces an isomorphism onto its image. So we have an isomorphism of this space with the following space. So we take the set of tuples indexed by the fixed points in these local spaces, the set of tuples that satisfy the following. So we want rho xe at mx to equal rho ye at my for all edges e, such that x and y are in the closure. So this is the theorem. So if k equals c, this is due to Goreski, Kottwitz, McPherson, and using almost the same arguments, you can prove that for any field satisfying this assumption, and it will be it will come up in a paper which is joint work with Jody Williamson, but it's more or less the same arguments. So, okay. Now this theorem motivates the structure of a moment graph and the notion of a sheaf on a moment graph. Pardon me? Well, I think it's quite restrictive, but the sheaves, I will define a good category of sheaves in a moment for which this always holds. So the only sheaves that we need a certain category of sheaves, and for those the hypercohomology is always free. So it's not a problem for us for these applications. So what is a moment graph, or what is the graph associated to this situation? So it's defined as follows. The vertices are the fixed points. So the T fixed points are in G mod B. The edges are the one-dimensional orbits. And because the closure of an orbit picks up two fixed points, this can really be considered as an edge of the corresponding graph. What we also need for the graph is a set of labels. So we label the edge E by the character alpha E in X. So a moment graph is a finite graph where each edge is labeled by an element of a lattice. So what is a K-sheaf? On G. Well, a K-sheaf is something which, I mean, which is modeled after the result of this this calculation here, after this theorem. So a K-sheaf is is an object M which consists of first Mx, an S module. So S just is the symmetric algebra, just to remind you, over the field K. That's where the field K actually comes into the picture. So Mx is an S module for any vertex x. Me is an S modulo alpha E S module for any edge E. And thirdly, we are given maps rho xe from Mx to Me if x is a vertex on E. And this, of course, is a homomorphism of S modules. So this is the data of a sheaf. And this can be made into a category in the obvious way. The objects are these sheaves. The morphisms are given by morphisms on each space associated to a vertex, on each space associated to an edge. And they should be compatible via these restriction maps, rho xe. So there's an obvious notion of a category. And what we did with the sheaf here, by forming these local hypercohomologies and defining this map rho xe, what we did actually is we defined a functor W from this category of equivariant derived category of sheaves on G mod B, to the category of sheaves on G. So each sheaf should have global sections, and that's very easy to define here. So there's a notion of a space of global sections. So there's a functor gamma which takes a sheaf M and gives the following space. So we take the set of tuples, elements in the direct sum of the modules sitting on the vertices that satisfy the condition that we have here in the localization theorem. So these two maps should coincide. So the elements, if you apply these two maps to the elements Mx and My, they should coincide for any edge E that connects the vertices X and Y. So now, if we want, we could reformulate the localization theorem, the theorem here, as saying that under these assumptions, the cohomology of the sheaf F is given by the global sections of the sheaf on the graph associated to F. So you take a sheaf F, and then you define this as the stalk WF upper X, so the stalks of the hypercohomology. Then on the edge, you take this local hypercohomology, and then you define this map. So this is just a reformulation, but now you see maybe somehow more clearly what we need to do in order to calculate this hypercohomology. We have to describe these sheaves on the moment graph. We have to describe these objects. Okay. So and the next step now is to define the right category of sheaves on G mod B that we need for the representation theoretic applications, and that have a very good description in terms of the moment graph. And this is a notion which is very recently was very recently invented by Jody Williamson, the notion of a parity sheaf. This is the wonderful thing is that it's rather independent. I mean, the notion and the category, the definition is very independent of the ground field. So the good category of sheaves on G mod B is called a parity sheaves. So what is a parity sheaf? So first, a sheaf in this category is called even if I'm sorry, I have to change notation slightly. So G mod B, remember we looked at the fixed points of G mod B, but now we somehow enlarge this and look at the stratification of G mod B. So G mod B is of course, it is stratified by the Brugha cells, and now either we parameterize the cells by the unique fixed point that is contained in the cell, or by the Weil group. It doesn't matter. So we have this Brugha decomposition, and we define now EW for an element in the Weil group to be the inclusion of the cell. Now this is the inclusion not of the fixed point W, but of the cell, and then we define a sheaf to be even. We call a sheaf even if I upper star W F and I upper shriek W F are direct sums of constant sheaves in even degrees. So when F is called parity, if F or F shifted by 1 is even. So this is a very interesting subcategory of sheaves on X, which is studied in a new paper of Jody Williamson and Daniel Juteau and Karl Mautner, which is on the archive since last week, I guess. And also Daniel told me that he will talk about this category in his talk on Thursday or this week in this conference. So for the moment, I just state two theorems. The first is due to Williamson. For each W in the Y group, parameterizing our strata, there is a unique indecomposable parity sheaf PW with the property that the support of PW is contained in the closure of BW of the cell corresponding to W, and the pullback to the strata at W is a constant sheaf in degree 0. Constant sheaf in degree 0. So the uniqueness is actually quite wonderful and quite simple proof, and so it holds in much more general situation. But these parity sheaves, sometimes don't exist in certain situations. So for flag varieties they do exist. For toric varieties they do exist. For very important varieties they do exist. But there are examples where these just don't, where you don't have any parity sheaf. But if they exist, the indecomposables are in this way parametrized by the stratification, by the strata.
This is probably true for any Kac-Moody.
Yes. This is true for any Kac-Moody group. So those are the sheaves that really have, in the end, representation theoretic applications. But so one remark. For fixed W, so maybe I should put a little k here to stress the dependence on the ground field k. So if we fix W, then this sheaf PKW is just the intersection cohomology complex on the closure for if the characteristic of K is big enough. So if we fix K, then there's a certain bound on the characteristic such that these PKWs are just intersection cohomology complexes. And this is proven first for characteristic 0, where the decomposition theorem is used, and then it somehow follows for large enough characteristic. But here the precise bounds are just not known. So for any given positive characteristic, for almost any given characteristic, you don't know if there's an isomorphism between the parity sheaf and the IC complex. Okay, good. And another wonderful properties of these parity sheaves is that you can describe the corresponding sheaf on the graph very explicitly. Those are the sheaves that are the first appeared in the work of Braden and McPherson. So they are called the Braden-McPherson sheaves, and they have a very nice algorithmic construction in terms of the graph. So let me just maybe say a few words about Braden-McPherson sheaves. So these are now sheaves on the graph G. Okay, I just give you maybe the definition or the characterization. So for any W, there is a unique indecomposable sheaf BW on the graph now with the following properties. So first, BWX. Remember, a sheaf it has a stalk at each vertex. This is a graded free S module. So endow as with the obvious grading, and we want this sheaf to be graded free. And BW, W should be just isomorphic to the symmetric algebra itself. Then the second property is that if J is an open subset, so of W, so open just corresponds. The vertices of our graph, they correspond to strata on the flag variety, and we call a subset of the vertices open if the corresponding union of strata is open. So if this is an open subset, then the restriction of the global sections of this sheaf to the local sections, this is surjective. So these are just as the same definition as the global sections, but we only look at a certain subset of vertices. This is surjective. Thirdly, Bx to BWX to BWE. So the map rho xe, this is surjective. With kernel alpha E times BWX if E is an edge linking X and Y, and X is bigger than Y in the Brüher order. Bigger than Y in the Brüher order. So, and there's a fourth property. The global sections, they should map surjectively onto the corresponding stalk. Okay. So this is a characterization of the sheaves. It's not difficult to show that such a sheaf exists and that it's unique. More or less, these four properties, they give you an algorithm that tells you how to construct these sheaves on a graph. So it's just a very nice class of sheaves on the graph. So the next theorem, which is joint work with Jordi Williamson, again a paper which hopefully comes up very soon, is that if we apply our functor W to the parity sheaf PW, then we get BW. So, and then we should probably assume the GKM property. So the localization of the parity sheaves are given by the Braden-McPherson sheaves. Okay. That is somehow the topological side of the story. So in the last 15 minutes, I want to talk about the representation theoretic side of this story. And for this, I focus now on the affine situation. So I focus on a situation that is important for modular representations and critical level representations and quantum group representations at roots of unity. So and I will talk about the analog of Sergel's functor, Sergel's approach towards proof of the Cauchy-Lusztig conjecture. Pardon me? It was not, maybe not written down. I'm not sure, but you can. I'm not sure if it's written down somewhere, but it's somehow an immediate application of the correspondence between the intersection cohomology complexes on G mod B and the projective objects in category O, in the principal block. Okay, so for this, let me talk about the affine version. So instead of the finite Weyl group, here let me draw the reflection hyperplanes which give the reflection group of type A2. Instead of the finite Weyl group, we now look at the affine Weyl group, which you get by adding the translates of the reflection hyperplanes. And if you consider the affine transformation group generated by the reflections on all these hyperplanes, you get from the finite Weyl group, a root system, you get the affine Weyl group. So here we have the affine Weyl group, and then what we can also look at is curly A. Curly A is the set, so let's write it here, the set of alcoves. So if you remove all these reflection hyperplanes in this picture, the connected components are called an alcove. So each connected component is an alcove, and we have a set of alcoves. And if you fix an alcove, you can act with, well, the affine Weyl group acts on the set of alcoves in the obvious way. And if you fix one alcove, you can identify W hat and A as a set. But we don't do that at the moment. There are two more algebraic structures associated to these two sets. The first is the affine Hecke algebra. So the affine Hecke algebra so it has a basis indexed by the elements of the affine Weyl group, and here you associate the so-called periodic module. Defined by Lusztig. It has the basis indexed by alcove. So this is the periodic module. So it's a module for the affine Hecke algebra, the periodic module. So these are two very natural structures associated to this set. And maybe it is important to somehow stress that in the construction of both these sets, a partial order plays a role. Here it is the Brüher order. The Brüher order of the affine Weyl group as a Coxeter group. And here it's so-called the generic Brüher order, or the Brüher order at minus infinity. So one should remember these are two sets, two partially ordered sets, and these orders, they don't coincide. So if we identify the affine Weyl group with a set of alcoves using a fixed fundamental alcove, the identification will not be order preserving. For example, A, it doesn't have a lowest or highest element. So, okay. And somehow in the definition of these two structures, the order plays a role. And in fact, the definition here and here looks just the same. I mean, it's just a new definition, or a new use of this partial order. Okay, here we are now on an algebraic side, but there are, of course, categorifications. So that's curly H and curly M. And of course, they have various.
Is it related to this semi-infinite?
Yes, it should be, yes, but I don't know much about. But that's the new order. Yes. So these are categories. So this is on the categorical side, and so they are related to the affine Hecke algebra and the periodic module, in a sense that those form the Grothendieck groups of these categories. So this here is the Anderson-Janssen-Zörgel category, defined in the blue book on their proof of the Lusztig conjecture and the relation between representations of the small quantum group and of a modular Lie algebra. This is the Anderson-Janssen-Zörgel category, which somehow categorifies the periodic module. And here we can take a lot of different realizations. For example, intersection cohomology sheaves, simple perverse sheaves on a Fleck variety with coefficients in the complex numbers would be a categorification of the affine Hecke algebra. But also the parity sheaves for any k, or the Braden-McPherson sheaves on the Breuer graph. So these are all categories that are related to the affine Hecke algebra. and now let's look at the map here, which sends W to W applied to AE. So we fix an alcove AE, just any alcove, and then we can map W hat to the set of alcoves. So it's a very, very simple map. And this corresponds to the action morphism from the affine Hecke algebra to its module. So we let X, just X, act on the basis element corresponding to the alcove. So M is a module for the Hecke algebra, so any element, fixing any element gives us a map from H hat to M. But now there's a functor which categorifies these two maps. This is a functor which relates these categories of sheaves on whatever to the Anderson-Janssen-Zörgel category. So this is this you find in a paper which I put on the archive in 2007, which is called sheaves on affine Schubert varieties. Modular representations and Lustig's conjecture. So it's on the archive in 2007. This functor is at the heart of this paper, and it's the technical heart of this paper, and relates sheaves of k vector spaces on an affine Schubert variety to representations of the Lie algebra over k associated to the Langlands dual root datum. So okay. Okay, so now let me talk a little bit about, more precisely about the connections and conjectures and theorems that you can prove using this approach. First of all, we have now this functor from H to M, and this M, it gives three categories. So it gives a modular representations if the characteristic of K of our ground field is positive. It gives quantum group representations if the characteristic is 0, and this is the work by Anderson, Janssen, and Zörgel. And there's an ongoing project, so it's not yet finished, together with Tomoyuki Arakawa. So we want to link this category to critical level representations of the affine Kac-Moody algebra associated to G. And here, of course, the input is either K parity sheaves or Braden-McPherson sheaves. And using these relations, you can link topology to representation theory. Okay, so finally, on the graph, you can somehow unify various conjectures in a very simple way. For example, the original Kashtan-Lusztig conjectures for finite dimensional complex Lie algebras or symmetrizable Kac-Moody algebras, or the Lusztig conjecture on characters of modular representations, or the Fiebig-Fraenkel conjecture on the characters of critical level representations of the affine Kac-Moody algebra. They are all unified in the following conjecture. Suppose WK is a GKM pair. So W is an element in the affine Y group. And what does that mean? It just means that on a certain subgraph whose edges are given by all elements of the affine Y group that are smaller or equal to W, the GKM property should hold with respect to K. This is a real, if you let W grow, then you have to exclude more and more primes, and finally you have to include all primes. So this is really a restriction. Suppose this is a GKM pair, then the rank of BWX, remember this is a free S module, of graded free S module of finite rank. This should be given by the Kashtan-Lusztig polynomial evaluated at 1. It should also be true in a graded sense. So the graded version should also hold. But let me formulate it like this. So the theorem now is that the conjecture, so this is the main theorem in this paper from 2007, the paper I mentioned above. This conjecture.
But again, probably conjecture can be stated for any one group, not for that.
Yes, for any Y group. Yes, for any crystallographic Y group, in order that you can change the field. But for any Y group in characteristic 0.
Is it true for finite?
For characteristic 0, yes. For positive characteristic, it's not known. But I state all the known instances in a moment. The first theorem is that the conjecture implies Lusztig's conjecture. Lusztig's conjecture on modular representations of reductive groups. And it also implies the Kashtan-Lusztig conjectures and the Fiebig-Fraenkel
with some restrictions on P, on prime numbers.
Thank you, exactly. This restriction exactly gives the restriction that Lusztig formulated in his conjecture. So for the application to Lusztig's conjecture, we only need finitely many W. And for those W, we are in a GKM situation if and only if the characteristic is bigger than the Coxeter number. So that's where the Coxeter number occurs again. So this is in complete accordance with what Lusztig conjectured. So, and the last theorem.
So you have some combinatorial interpretation of the appearance of Coxeter number here, just because of combinatorics of W affine, right?
Yes. That's just you just look at the affine root system, and it's not just the combinatorics. So the known instances. So this is in a series of papers in the last years. First of all, the conjecture is true if the characteristic of K is 0. I mean, this, of course, it was known before because these BW also, they encode the intersection cohomology complexes, and this was known before. So in characteristic 0, everything is proven using the decomposition theorem and everything. But now the conjecture is also true if the characteristic of K is bigger than an explicit number depending on W. So a number that you can write down, that you can calculate, which depends on W. So there's an actual bound on the exceptions. Unfortunately, this number is huge. This is amazingly huge. For example, in the type A8, where this conjecture should be true for Lusztig's conjecture should be true in type A8 for each prime bigger than 8 or 9. 9, I guess. It doesn't matter. It doesn't matter. Okay. But this number has about 40 digits. So it's very far from the Coxeter number, also already in very low rank situations. It's a huge number. Okay, and then finally, the multiplicity 1 case of this conjecture is true. And this means what you can prove is that BWX, this is free of rank 1 if and only if the corresponding Lusztig polynomial evaluated at 1 is 1. So if either side here is 1, then the other is also. And this holds for all k.
But this theorem is only for arbitrary.
Which one? This one? For arbitrary crystallographic. Crystallographic Weyl groups. What I need is that the coefficients here are positive, are non-negative of the Lusztig polynomial. That's
so
the only
point W have in conjecture any crystallographic.
Yes, yes. W. So W is any crystallographic Weyl group, or even any Weyl group, but then you take K to be of characteristic 0. Then this is not proven. This holds only in the crystallographic case.
Can you do it for translations? For translations, so when the Lusztig polynomials are extremely simple, actually.
If W is a translation, I haven't tried, so I haven't looked into that. I'm not sure if you can prove this conjecture for if W is a translation. I haven't tried. Okay, so thank you very much. That's what I wanted to say.
Thank you. Questions or comments?
Quick question. There is a construction due to Sergel and now Sergel-Havan, right? You do something similar what you call topology, right? Shifts on the graph, right? But you consider bimodules. And then as we know, Sergel connected it directly, Sergel obtained some kind of nice categorization of affine Hecke algebras in terms of bimodules over polynomials which grow actually absolutely the same way as your S modules.
Yes.
Can you comment on it, please?
Yes. So there's an equivalence of categories, at least if the characteristic of K is 0. So the Sergel bimodules form another categorification of H, and they are actually equivalent to the category of Braden-McPherson sheaves on the graph. If the characteristic of K is 0, I mean, they are very, very similar, but somehow the advantage of the graph is that you can that you have a better control over the primes. So you can look at subgraphs and somehow restrict, look at fields with a very small characteristic.
You didn't even mention bimodules, right?
No, that's true. But it's an equivalent category. That is true.
So it is doable, right? So we can spell everything in characteristic P, right, and do something else, right?
Well, the problem is in characteristic P and in the affine situation, the representation is not anymore reflection faithful, which is one of the ingredients in Sergel's category. But I'm sure that this can be overcome. I think if you want, you can translate everything into Sergel bimodules. I'm pretty sure about that.
In this middle case where you, on the board where you go to a quantum case, you take characteristic 0.
Yes.
Couldn't you take the mixed case where you go to a root of unity and a characteristic 0?
I don't know. So because you mean this an analog of this functor? Yeah. If you know the subgeneric cases, that somehow the philosophy, if you know the subgeneric cases explicitly, then there might be a way. That's the approach we have here. So we first looked at the subgeneric case, and now we are trying to glue all the subgeneric cases together to get this description, which is given by this category. And I believe that this should be also true in the quantum group and positive characteristic world. But I guess this is quite open. I don't know.
Any other questions? Let's thank Peter again.